The Indian Association of Structural Engineers, also known as IAStructE, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IAStructE is registered under the Society's Registration Act 21 of 1860. IAStructE is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAStructE has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. IAStructE is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAStructE has collaboration with various international professional like-minded associations and institutions like IAStructE, UK and FIB for strengthening global connections and professional exchange. IAStructE's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAStructE endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAStructE is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAStructE's activities are widely appreciated and known for quality technical contents. IAStructE is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. IAStructE's publications are becoming popular with time. IAStructE has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAStructE started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, IAStructE launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. IAStructE is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. Joining IAStructE offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IAStructE has its student chapters in several leading engineering institutions as well. Membership of IAStructE is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IAStructE is available on its website www.iastructe.co.in.
Hello, Vikas, my voice is audible?
Yes, sir. Yes, sir.
Dear friends, welcome to the webinar. Today's topic is learning from structural failures. The speaker is a very learned person, Professor P.G. Venkatram. He graduated from IIT Delhi, IIT Madras in 1981, and thereafter master's from Carnegie Mellon University, United States in 83. Now he is former chief executive of L&T Infrastructure Engineering Limited and currently advisor technical services at ASSYSTEM India Private Limited. Brings over 42 years of his distinguished experience in bridge engineering. He has designed structures ranging from simple slab bridges to complex cable stayed and extradose bridges. He serves as key person in IRC committees like B2, B4, B9, and is professor of practice in IIT Madras. His expertise also spans designs and construction of aqueducts, chimneys, cooling towers, TV towers, aircraft hangars, etc. Brief about the topic. As we know, the structure failure would result when a structure or component loses its ability to perform the functions due to excessive stresses, deflections, or loads. The recent spate of bridge failures during construction across the country has highlighted critical gaps in our planning, design, execution, and supervision practices. These incidents span a wide spectrum of bridge types from relatively simple girders, slab structures to more complex segmental construction systems. These failures serve as important learning opportunities for the engineering community. They tell the need for rigorous design, checks, robust site supervision, proper training of personnel for upgradation of skill, adherence to safety protocols, and the implementation of the real-time monitoring system during the construction. Now, I request Professor Venkatram to proceed. Professor Venkatram.
Thank you, Dr. Dhawan, and thank you to all the participants. Let me start the presentation from my side. Just can you please somebody confirm that the slideshow mode has started on?
Yes, sir. Yes, sir.
Okay, fine. So This is about around 35-40 slides and about 15 to 20 failure cases. Some of them are similar and have a common thread. I'll make an attempt to make sure that I at least point you, no failure is due to one single cause normally. Quite often there are common threads to most of these failures. I will try to take you through what I have judged. Some of them I know because I was participant in the investigation, and some of them I have reviewed the documents, and some of them are my best judgment of what could have happened. And in many cases, I'll try to suggest how we could have prevented this. Most of them, I should say, are preventable. So let me start with some introduction. So about 95%, and excuse me if the theme is structural engineering, but since my experience is primarily in bridge design and construction, so all my failures are linked to that. So excuse me if I don't deal with buildings. I have limited or near zero experience as far as they are concerned. But nevertheless, many of the issues that we discuss here may be applicable there also. I leave the audience to suitably apply the knowledge gain. Okay. So about 90 to 95% of the bridges constructed in India, they will fall under this category. You either do a cast in situ construction wherein 100% of the concrete is poured in situ, or you have precasting. Precasting again, partly like girder and slab, or a fully like segmental, or a mixture. Almost all of them, or some of them, they have significant precasting and a very small in situ construction, or a completely in situ type of construction like slab. And remember, most of them I'm talking about is with respect to concrete, because even today, almost more than 95-96% of the bridges are made with concrete. Steel constructions are prevalent, but they are very selectively used primarily because of the cost of construction. So we will see some of it, a few examples of that also here. So when you look at this as the overall spectrum of constructions that we adopt in our country for the bridges, I'll take you through statistics. It's a report published by CRRI, a statistical study of reported failures. Please understand that in the 40-year period from 1977 to 2017. Don't assume like statistics that in these 40 years only these 123 failures took place. These were reported and published. And they were categorized into two type of data. One is on the nature of the bridge arrangement. RCC and PSC dominate. About 80% of the failures have taken place in that. Steel, Bailey Bridge, which is another steel composite, again involves steel, and one unknown, possibly it might be a masonry structure. It is not elaborated, nor it is of interest to, but essentially to understand that roughly 80% of the bridge failures that have taken place are in RCC and PSC, and remaining 20% around in steel. And also, if you look at the nature of the cause of failure, what are the different causes under which these failures have been categorized? If you take a look at it, other than disaster related design fault, okay, other than these two, which is about 27 out of 23, about 25% of them, the remaining 75 to 80% are all related to construction, scaffolding, construction technology, mechanical failure, human error, and some unknown causes. Now, if you leave out the disaster related primarily failure caused by natural events, say maybe due to earthquake, maybe due to flash floods, maybe due to strong winds, something on which we have partial control. We don't have 100% control, but partial control. So if you look at it in terms of design and construction, about 5 to 7% of the failures can be ascribed to design faults. Significantly larger number, 80 to 95% of the failure has to be associated to construction activity, either during or post-construction activity. Now, again, I would like to take you through to not look at it as statistics. I mean, looking at the left chart, one might start thinking that RCC and PSC structures are possibly dangerous to construct. I think you should disabuse yourself of that opinion, because 95% of the bridges are made of reinforced concrete or prestressed concrete, and therefore the number of failures are likely to be in that. What you should tell you again more is, if you look at the small fraction, which is the steel construction, and you see such a huge percentage of them showing failure, it tells you actually that steel construction is far more riskier from failure point of view than concrete. That is not to justify either any one of the failure, but not to draw wrong conclusion that RCC and PSE bridges are riskier to build. Okay, so having seen this background of statistics and see what are the variants, 80% from this data, published data, suggests construction as the root cause or root time at which these failures take place. Now, I will take you through a few sample examples. The first example is something that I classify as a design failure. It's an incident that took place somewhere in 2002, about 24, 25 years back. It is a very simple construction. It's a road over bridge, as you call it, across, and it's a 40-meter PSC box girder. And the incident was that as soon as the construction was one of the most simplest form of construction you can think of. That is basically putting up staging, then putting up shuttering for the box girder, cast the box girder, thread the pre-stressing cable, and stress it. As soon as they finished stressing, the girder, where you can see this cloth-like shield hanging, the girder cracked from top to bottom, and the deck slab looks like this at the end of the failure. Now, the design was reviewed, and the design in service condition was perfectly correct. But where they failed to make the problem was, though it's the simplest form of construction, we quite often look at it, the stressing sequence did not take into account that when they apply the full pre-stress, the self-weight is not fully mobilized on the bridge deck itself. As you can understand, during the construction process, 100% or other than the small portion of the weight which is resting directly on the two piers at the end, about 90-95% of the weight is sitting on top of the staging. And the staging is an elastic material. And under the weight of the box girder, this elastic material deflects. And when it deflects, and when you pre-stress it, and as everybody would have taught you, when you pre-stress the girders tend to hog up and lift off from the support. The correct expression should be, it will attempt to lift off from the structure supports. And when it attempts to lift off, the load on these staging will get relieved. And when that gets relieved, what happens is it will try to recover the compression, elastic compression that it has gone through. Now, depending upon the hogging of the girder to the compression of the box, you will get a situation where it will be completely lifted off or partially lifted off. However, most designers tend to assume that the self-weight is magically mobilized. Self-weight can never be magically mobilized. So what happened in this situation was the self-weight was never fully mobilized, and the design checks were shown as if the beam was simply supported for the self-weight. Now, where is the design flaw? The design flaw was in not integrating the construction methodology into the appropriate design check. What they should have checked was, how much of the pre-stressing should I do when the weight of the girder is on top of the staging? Now, you can argue that finding out what percentage of weight is on top of the staging is a very complex exercise. Yes, no doubt about it. But then they could have alternatively gone through a checks to say, how much pre-stress do I need? Remember, design pre-stress is for not only self-weight of the box girder, the subsequent superimposed dead load, and the subsequent live load. So the application of pre-stress is meant for much larger flexural forces than for the self-weight alone. So they could have also estimated how much is the pre-stress necessary to make sure that it will sustain the self-load, apply only that much pre-stress, and then decenter the, you understand the concept of decentering. Basically, you remove the supporting staging sequentially from its span to the end so that the self-weight is fully mobilized, and then continue with the remaining pre-stress. So this is a common mistake that you will notice in almost all the pre-stress design, where they do not integrate how they are going to build the bridge into their design check. They will assume. So ideally, I would have expected the drawings to show that you stress these cables and then introduce a term called decenter the structure and then continue with the remaining stressing. That would have been the correct design procedure. Then the site would know the intent of the designers. And that's why I have classified that under this failure under a design failure. Of course, nothing much was done. All the pre-stress were dismantled, removed. This portion of the superstructure was dismantled and the ducting reconnected and then stressed again. The same structure was used, re-stressed again, but this time with the proper sequence, with the proper decentering, and the bridge is standing now for more than 25 years. So the problem here is how you dictate the stressing sequence in the drawing. Never make the assumption that pre-stress will hog and therefore the full dead load will be mobilized. Full dead load will be mobilized based on the construction methodology and construction sequence. That's an aspect that designers need to take imbibe into their mind and accordingly put the correct construction instructions into the drawing. Okay. The next example is another design failure issue is the instability issue. This is in that time it was a very famous failure in 2014. It is a curved span on an approach to the cable stayed bridge in Surat. What happened was, as you can see, the curved box girder was cast on the staging. The collapsed staging is lying below. And when they were carrying out the stressing operations, the radius of curvature of this span is from, if my memory serves me right, was somewhere around 60 to 80 meters radius of curvature, almost a 90-degree curve in a very narrow and tight space. And as you can see on that plate, the bearing spacing is the same as that for near straight spans. Now, as soon as they finish the stressing, now what are the situation? What are the cross section? The cross section is symmetrical about the curved center line. The pre-stressing is also symmetrical about the curved center line. You must understand one thing, that this 4-point support for any span is an indeterminate support, and it requires a careful stressing arrangement to make sure that the bearings don't lose the compressive force. Now, please remember that the failure took place in 2014. The design is a much older vintage. When I say the older vintage, it was, from my knowledge, the design was done somewhere around 2003, 4, 5 period. Construction was very long term stretched. Why I'm making that point is, in 2004 and 5, in IRC standards, there was no definition of how do you check the equilibrium. The evaluation and the checks for equilibrium were introduced in 2009. And what happens is, and so then you can ask a question, so then what were the engineers doing? Engineers were doing a wide variety of things. Some of the most common things that was done in those days was to do analysis and evaluate if all the 4 bearings are in compression. Now, that is not sufficient for today's checks, but that was one of the checks performed. And the problem with that is, when you have a curved structure like that, your pre-stressing operation itself redistributes the reaction between the girders. Though it is simply supported, it redistributes the reactions between inner girder and outer girder. As you can visualize, a vertically draped cable, if an equivalent load method is equivalent to an upward load, it will alter the reaction. And since the force support structure is an indeterminate structure, it will redistribute the reaction. In that process, one of the bearings lost the compression and the whole thing toppled over, and maybe, I don't know, there was a significant amount of loss of life. Now the question was, what could the engineers have done? Normally, if you take a look at what the design standards, why do these things happen to us? Because as a country, we have decided that all our project implementation will be a compliance-based implementation. What does that mean? It means that if it is a design and build, there'll be design specifications. And what are the design specifications? It will be either covered exhaustively in the tender document, or it would be referring to the relevant IRC standards. Now, in 2003 and 4, verification of equilibrium was not covered in IRC standards. Then what should the engineers do? That's where the question comes, good engineering practice. The good engineering practice is what is not covered in the code. We should look at how the equilibrium verification is done in the other code. They could have looked at BS 5400. It tells you that you must ensure that the factored overturning moment is less than unfactored restoring moment. Listen carefully, factored overturning, because it's a stability is a failure condition. So you do the checks in ultimate limit state. So that is why you use a factored overturning moment should be less than the unfactored restoring. This they could have used from BS5, unfortunately not done, and we ended up facing this failure. Now, what has happened is that in 2009, through an amendment, notification number 53, basically we introduced this verification of equilibrium, which is now formally put in as a part of table A, B, if I'm not mistaken, ABC or B1, B2, B3. In that form, it is present in IRC 6, where you can see that the overturning factor is 1.05 and the restoring factor is 0.95. I've only reproduced the dead load part. You have to also consider other effects, live load, pre-stress, construction life, whatever is there as a part of your stability exercise. Now the question is, this came about as is bound people, and we say if it is not written in code, I don't need to do it. So I will show you a few examples where you follow the code blindly. You will also get into trouble. Our codes are not that well written in certain other aspects. Okay, so this was the issue with stability verification. Now, the next example of a failure I wanted to take you through is the deck slab of a road over bridge in Nandnagari in Delhi. This bridge, as you can see, road over bridge is a steel concrete composite with steel girders, steel cross diaphragm, and the deck slab. You might say it's a very common construction, but the difference between this and the others is that this deck slab was a fully precast deck slab with an in situ stitch pour on top of this diaphragm. And if you want to know approximate size of this concrete panel, the spacing of the longitudinal girders is approximately 3 meters, and the spacing of the cross diaphragms is about 5 meters. So this panel, the full precast panel, is approximately 3 by 5 meters. 3 meters in the transverse direction and 5 meters in the longitudinal. Next important to know is, how was this cast? This was cast on the ground in a casting yard. And how was the casting done? All they did was they laid out pre-stress, your flooring tiles of 1 feet by 1 feet that was laid. Side shutters were put, reinforcement cage was lowered, and the concrete was poured. How do you also have an evidence of this? If you look at the left side, this is one of another panel which hasn't failed like this, but it is on the way to failure. It hasn't failed like this, but it's on the way to failure. What you can see here is that you can see the pattern of the 1 feet by 1 feet, that 30 centimeters by 30 centimeters, the tiles that were used at the bottom form up on the ground. It started off there, and gradually you can reach this situation where with the passage of load, you can see this lot of these lines. These are nothing but moisture marks, and these moisture marks are following the line of the reinforcement, and basically they are cracks which follow the line of reinforcement. Now, nothing can be simpler than casting the slab on the floor, and yet you are having this situation. And this situation happens because of the poor quality of concrete. So one thing you must understand, concrete derives its strength and performance not only from mixed design. It also derives its performance characteristic from its flowability, which we call it as workability. It also derives its strength from an aspect parameter called vibration. So if you just mix it properly and don't have proper flow characteristics and proper vibration, you will not get the desired strength. Now, when it comes to workability, you must also have the appropriate workability and appropriate vibration methodology, which ensures that the concrete flows around all the bar so that it has a good bond. So those of you who have studied the IRC 112 as well as IS 446, you would have noticed that there is a section on how to judge whether which area of the reinforcement concrete can be having good bond and how of them are poor bond. Now comes the question, what has bond got to do with it? Remember one thing, a reinforced concrete suction works like reinforced concrete primarily due to the one fundamental property, which is the bond between concrete and reinforcement. Now, what has happened in this is, while they have precast the panel, so one would automatically think precasting means the best quality production. Fine, best quality, fine, it looks everything fine. But however, cracks have followed the lines of the bar. This, whenever you see, my advice to you is whenever you visit your site and every time you see a crack pattern that follows the line of reinforcement, you have a serious trouble ahead of you. What it means is your concrete is has undergone, I shouldn't say undergoing, it has undergone during the initial setting process what is called as a plastic settlement failure. What does plastic settlement failure mean? What it means is once you pour the concrete and leave it there, the heavier particles of the concrete tend to settle down under the action of gravity. And when they are settling down, they will encounter this reinforcement in two directions. And when they encounter the reinforcement in two directions, they need an assistance to go around it. And that assistance is provided by us practicing engineers in the form of vibration. So if you don't vibrate it properly, you allow the concrete to naturally flow around it. There are other ways to go around it. You can overcome, no, I don't like vibration. So then you go and have to then do what is called as a self-compacting concrete, which means you don't need vibration. The concrete doesn't need the assistance from mechanical assistance to go around the rebar. But you're using normal concrete and your workability is such that it is not able to go around it, and you as a practicing engineer are not assisting in going around the bar, then what will happen is you will find that the rebar and the concrete have got poor bond or no bond at the bottom half of the reinforcement. So far, so good. When it is having self-weight, you know that in bridge decks like this, self-weight is hardly 5 to 10% of the design forces. Major forces come when the live load starts to move on it. So you will not notice it during the time that the bridge is under construction. But once the live load starts to move on it and the bidirectional bending moments start appear on the slab, then the bond between the reinforcement and concrete starts to get tested. The heavier the load, heavier the testing. Lighter the load, lighter the testing. Now comes the question, over a period of time, depending upon because the road traffic is unpredictable. It is, you can't say every day at this time, this kind of load will go. No, it will randomly go. So when it goes, for the lighter vehicle, what it will do is it will test the bond. The bond might fail and it becomes, instead of becoming reinforced concrete, it becomes reinforcement and concrete. So then what happens is there is no RCC action. There is only a PCC action, and under the flexure, the concrete in the bottom is trying to resist the tension, and the weakest place will be where there is no concrete and which is around the bar, because there is no bond between them. So flexural cracks develop along the bar because it's like a section with hollow, and the hollow point is where you will have the least section property. So with that in mind, the cracks start developing until one day heavier load comes in. This may happen through lighter load. Lighter load, I mean passenger cars, even public transport buses are light loads. But if you have trucks carrying freights, goods, etc., once they start going, at that time they test this so much that the concrete automatically gives way fully, and then you end up with this. There is no cure for this disease. The only cure for this disease is you have to dismantle the slab and reconstruct it. That's the only solution left. And I have seen, in my career, I have seen this kind of a failure in at least 5 bridges. Personally seen it. And this is one of them. And you can notice that you can ask a question, why is it that there is no such failure here? Possibly this is due to the reason that this is not in the wheel path. You remember that in every traffic, there's a particular path which majority of the vehicles will follow on a lane mark. So it is possible that this is where the wheel path is. This is away from the wheel path, so it is not tested. Not that this will not go in that direction. So one way to identify, remember the sad part of it is, you'll be able to identify this only after the vehicle starts flying on it. And once you have this solution, this situation on hand, cracking due to the plastic settlement of concrete during the initial setting phase, due to poor vibration, it's an avoidable problem. It's an avoidable problem. Poor vibration, then you will end up having to dismantle this slab and rebuild it. Now comes a crucial question. Why can't anybody vibrate the slab properly? If I were to ask this question, I am very sure vast majority would say every concrete is vibrated. I agree with you. What is the mode of vibration that most people use, which I have also seen in the sites, is a needle vibrator. Now there comes a question. This is an area element. That is a panel which is 5 meters in this direction, 3 meters in this direction. when you have an area element, how do you best vibrate it? This presentation I have meant as an introductory, as a what you call sensitization presentation to many field engineers. Almost invariably, everybody says, other than need oil, you should have used a screed vibrator. My next follow-up question invariably is, which project site have you seen bridge deck slab being vibrated with screed vibrator? Then comes the deafening silence. Screed vibrators are rarely, if at all, used. Okay, alternative to screed vibrator, what is it? You can use form vibrator. But the question is, form vibrator attaching motor at that height and doing the form that depends upon the nature of construction. I'm assuming that if you're doing in situ construction, form vibrator is possible. Now, screed vibrators induct vibration with a very large jerky motion, which means that your staging supporting system needs to be sturdy. Now, we have not prescribed anywhere that we must do. Needle vibrator, is it not impossible to vibrate slab? Yes, it is possible to vibrate slab. But the question comes, what is the efficacy range of a needle vibrator? This question, if you ask in a public forum where people at site are sitting, invariably you will get a silence because most people don't know. The issue is the efficacy range of a needle vibrator is between 15 to 30 centimeters. That means 6 inches to 1 feet, depending upon the diameter of the needle and the energy it is transmitting. Okay, fine. Now, if I have a 3 meter by 5 meter panel, how many needle points should I put up? You'll automatically guess that I have to do almost 10 by maybe 15, about 150 to 200 points I have to do. Then next comes the question, how much should I vibrate? How long should a needle vibrator be operated in one spot? This is also engineering, this is also science, this is also knowledge. The question is, most people don't know, and every time I have gone to the site, I turn the other way around for a simple reason. I don't want to be critical of everything that is being done. The needle vibrator, once it starts, it's never switched off, nor is it taken out. It is used for vibration, it is used for pushing concrete, it is used for all kinds of activities. All the standards in the world where you have to use the needle vibrator, it says you have to be between 5 to 15 seconds. 5 to 15 seconds, depending upon the workability of the concrete, density of reinforcement, etc. So it is also an art form. Now, question comes, are we ignorant about it? No, I'm not saying we are ignorant about it. I'm only saying because we have framed the rules of project implementation in such a fashion that I have only got to comply with my code. I don't have to do anything beyond the code. Code doesn't define these things to you. Why should they define it? This is something meant to be just like, as a designers, you need to know a lot of new things. As a site people, you also need to know things which are not taught in the class. So you need to continuously learn. And therefore, when you have to identify the type of needle vibrator, the extent of its usage, etc., it is a knowledge that is required at the site. Now, if you don't do this properly, you will end up having this kind of a situation. So, this is only an extraction of a good bond condition and bad bond condition. You can take a look at IRC 112 clause 15.2.3. It will tell you. And fundamental reasons for this are primarily linked to thickness, flow of concrete. Remember that direction of concrete is important. And the code takes care of certain aspect from anchorage length and bond characteristic, but it cannot take care of you of a total negligence. Okay, so partly taken care of in code, that doesn't mean you don't have any responsibility for vibrating. That is what I want to dispel. Now, who takes care of all this? How do I take it? It is not mentioned in any work specification. You take a look at ministry's orange book. Even orange book gives you no guideline. How long to vibrate? How long the needle vibrator should be? What is the efficacy range? Nothing is clearly mentioned anywhere. It simply says it should be adequately vibrated. That's all. And after that, the definition is left to you, me, anybody. And as everybody say, there's a popular expression in Hindi, we do a lot of things Ram Bharose. So वैसे ही होता है. Okay. So we need to, if you vibrate the concrete, you will avoid that problem. Let's move on to the next. This is an example of a bridge in Varanasi. It happened in May 2018. The girders have been erected. It is not a very long span. It's a 30-meter girder. And what you can see is, you can see at the back of it, there's another span which has been assembled in the same fashion that is standing there, whose deck slab has not been concreted. And if you take a look at the supporting arrangement below this girder, below this girder, below this girder, and here, you will notice one thing. Girders are all same, but they all have randomly different arrangement for support. I use the word randomly different because if it's an engineered support, they would be very similar to each other. Unfortunately, during the erection process, after the erection process, these two girders have fallen down here. And sometimes when we investigate these and take a public position, I feel quite often it is better to say, I made a mistake. It is far easier than otherwise it makes the whole industry look foolish. From my memory serves me right, the falling of these girders was blamed on strong winds. Now, okay, fine, possible. I'm not denying that possibility. An unanticipated gust or something could have created, but it defies logic. If you notice, these two girders have fallen this side. If these two girders have fallen this side, it will tell you that if wind was the cause, it must have come from our right-hand side. And if it was on the right side, why did it leave these three girders in place? And since these girders are so placed, why is the wind high on this? So sometimes along the line, basically, they have not taken care of adequate bracing, no temporary condition, very poor support arrangement. And you cannot leave girders like this for long without a bracing arrangement. And I can tell you, in the name of bracing arrangement, I will show you a few examples of what all people do. None of them are good enough. None of them are good enough. And after seeing a lot of these, and remember, girder and slab, precast girder and slab is one of the most common method of construction in the country. It's the cheapest form of construction. And there are rules to be followed for this, precautions to be induced, stabilizing arrangements to be defined. So these are all the aspects which we as engineers need to make sure we show adequately in the drawing. After many of these failures have taken place, in a pretension girder specification of IRC, a concept of stabilizing arrangement during construction has come. And it is a sad state of affairs that people will do it only if told to do so. Why? I come back to the same concept. We are a compliance-based implementation country, where you say if the rule book says do this, they will do. If the rule book says does not mention it, I need not do it. That's the approach that is taken. And hence we have all these issues with the failure. So this is a preventable accident. It could have easily been done by adequate bracing. It should at the very least be mentioned in the drawing. I also know designers hesitate to put things which are beyond. If they mention it in the bracing, then the question will be asked, what do I design the bracing for? And once that question is asked, then you need to go into the construction methodology. What will be the construction sequence? What will be the construction methodology? How will they support the deck shuttering? How will they pour the concrete? What will be the sequence? What will be the imbalance caused by various, all these activities needs to be identified before you can design a bracing system. It is not, if I put, we'll keep this in mind that this is a common failure in all these guy girders is inadequate bracing and temporary condition and very poor supports, all randomly put. Okay. Next, only in July 2023 did IRC issue a notification 60, and this is for IRC SP 71. And if you look at the code for IRC SP 71, it will be a pretension girder. Then people will also argue, no, that is my engine's post-tension girder. This code is not applicable to me. This was not meant to be that way. This was meant to indicate that these kind of precautions are necessary for you to make sure that your structure is stable during the construction stage. Remember that this came only in 2023. All that I'm showing are well before. However, it's like question, does somebody need to, what they call it, tell us not to touch a live wire? We don't touch live wire. No? We avoid doing it. In the same fashion, you don't leave the girders inadequately braced and supported. It should be a common sense practice. Unfortunately, it will be getting done only once we introduce it in a code. Otherwise, it is expected to be a normal practice, but unfortunately, all normal practices, unless they are codified, we will not follow. That's a sad state of affairs in the way we practice our engineering. We need to change this. Otherwise, we will have this repeating again and again. Now, the next example is a improper detailing. It starts with improper detailing. This is a bridge actually. It's a 5-span continuous bridge with the 2 end spans being 35 or 36 meters and all the interior 3 spans being a 55 meters. It's a post-tension girder. It's a 17-meter wide deck on a 2-girder system. And I'm not using the word 2-girder. The whole thing was cast in situ. And once your structure is continuous, what's the most important thing that you need to know is the fact that the support displacement or disturbances lead to redistribution of the reactions, right? So this bridge was constructed in around 2008. It started construction. 2011 or 12 it was finished, and in 2019 December this happened, wherein this pair of bracket gave way. Okay. And as you can notice here, there's virtually no reinforcement in this direction. Now, some details about it. The size of this pier is 10 meters. The center to center of these web is also 10 meters. The bearings is 10 meters. What does it tell you? The bearing load is almost on the edge of the column, on the edge of the wall type pier, if you want. I don't want to use the word column. Wall type pier, it's almost at the edge of the wall type pier. And therefore, there was a, I'm using the word carefully, and therefore there was a minimum reinforcement providing for the tie. And the reason for that, is the fact that in IRC 78 2014, this clause still exists, and it is a recipe for disaster if you follow it blindly. It says in case bearings are placed centrally over the column and in the width of base located within half the cap depth of the cap from any external face of the column, the load from the bearing will be considered to have been directly transferred to column and the cap beam need not be designed for flexion. Okay, this is what the code says. Now this I have reproduced it only for one reason. This code clause is absolutely, should I be blunt or polite? I'll say no, it is technically totally invalid. Okay, so with that, what happens is, when you have too concentrated load on such a wide column, you will have even if you visualize a simple half strut and half tie, you will realize that there will be a significant tension at the top. Now, this structure actually was giving a hint that something is wrong with me. All structures give that. And how do you know that? You know it from the fact that if you notice this dark stain is actually a cement wash covering a vertical crack. That means sometime during the early life of the structure, it had crack, and since the crack was very fine, they didn't bother about it, they just washed it. And to tell you the truth, this situation is not restricted to this failed pier alone. The same thing is there in every pier. If you notice through this gap, you see a similar cement wash in the next pier. So that pier also had a vertical crack, which means that there is a splitting tension here. There was an evidence of it, but nobody did anything about it. Now, what happens with this crack happens? When this crack happens, this pier tends to deflect. It is to crack and deflect. Once this deflects, what happens to your estimate of the reactions on the bearing? Since its structure is continuous, there will be redistribution of reaction. And once the redistribution of reaction goes place, some other bearing gets overloaded, and that tends to crack. And this way, the cap keeps on happening until such time that the tension in this tie bar exceeds. And on the night of December 2019, the heavy vehicle, one truck was passing by. We don't know which corbel cracked and gave way first. When it gave way, all the load got transferred, the other one also gave way. Fortunately in the design, they had a cross diaphragm which came and sat on the wall pier, and the whole bridge did not come down fully. From what I know, in 2023 or 2024, it has been restored the traffic. So for almost 4 years, the traffic was going on a temporary road here. And the point was this aspect. If you take a look at in IRC 112, what does it say? Whenever you have load on the edge, you still have to provide reasonably strong reinforcement, which is preventing what is, it uses the word sliding mechanism. You can use it as a strut and tie model. If you notice that, because here you can argue the shear span to depth ratio is 0. So there should be no strut and tie, but it is, you can do a strut and tie modeling assuming the column behavior and partially loaded column concept. So you have variety of analysis processes which are now described in IRC 112. What I'm trying to make a point is IRC 112 has rectified the design, but please remember that many of you still use IRC 78214, in which this faulty clause is still present. It is still present there, and so be careful when you're using it. So you have to make sure that your design principles are corrected. Okay, now we move on to the other kinds of failure which happens during the construction phase. This is an example of a launching girder failure. The launching girder fell, and what you see is a collapse of span is not because something happened to the span. It happened because the launching girder landed on it once its front leg failed. You can see the damaged or the failed front leg. It fell on top of it. So this is where you have to be very careful that our launching girder designs necessarily are not that robust because of the economic scheme of things. However, that is not to say that they don't have anything criteria or safety concern to be addressed, but they need to be addressed in such a fashion that they take care of all the design conditions carefully. And remember, the most dangerous part of any bridge construction is when you are moving a heavy load. When you are, as long as the load is static, the problems are less, not zero, but they are less. But the moment you start moving, whether it is a moving of the launching girder or whether you're moving with a heavier load on the launching girder, you start inducing the risky situations, and make sure your method statements are so carefully drafted and followed at site that you avoid all such failures happening, right? In July 2021, this is another type of, this is actually a 40-meter spine and wing construction wherein the spine is erected. What you see is a failure. This happened approximately 2 weeks or maybe 3 weeks after the span was erected, stressed, and the launching girder has moved forward and has also assembled the next span. After that, this has happened here. Now, you can ask a question, once the pre-stress is over, what is there for it to happen? The main thing you have to remember, one thing is that during construction, depending upon how you support the superstructure, in this instance, invariably they are supported on temporary steel packing, not on the permanent bearing. And at that time, when you do the steel packing, it induces its own frictional restraint. They may be the last straw. The question is, we'll come back when you look at another case where a very identical design, it had a much heavier failure. If you notice here, there's a crushing of concrete at the junction of the web and the soffit, and the crushing travels upward, but it stops. That is the failure in this package in July. But in August, a very similar design, a very, very similar design. In fact, I would say for all practical purposes, identical design, same, another package in the down stretch of the same project. Here, what happened is, at this location, similarly, as you can see, this launching girder had finished assembling this span. It had moved forward, had finished assembling that, and 20 days later, there was a crushing of this, and this whole span collapsed. This and the other one are identical in nature, identical in grade of concrete, identical in dimensions, etc. Then you can ask the question, why did that fail that way and why did this fail this way? The whole issue is the fact, you must remember, this is standing right now due to the presence of pre-stress, and the crushing is limited. Once the crushing is limited, there is still some residual pre-stress which is holding the self-weight, just holding. Okay. Unfortunately, in this situation, the crushing was so extensive that all the elongation that was induced in the cables were lost. So basically, the pre-stress vanished. And once the pre-stress vanished, there was no pre-stress to hold the self-weight even, and it collapsed and fell down. right? Now, the important question to ask is, this project was not investigated so much in detail, but this was. So what was done was a number of core samples were taken from the soffit slab, web, deck slab, etc., and their in situ cube strength were assessed. And if you come to know that this girder was designed with N55 grade concrete, a segmental spine, and the in situ strength, the in situ equivalent cube strength was ranging from 27 MPa to 70 MPa. 27 to 70 MPa. What was the condition of the test cubes that were taken during the casting of this segment? Very consistent between 63 and 65, which means quality control of the production of concrete was excellent. Quality control during pouring was terrible. Now you can come to and ask a question, what can we do wrong between production and pouring? Between the production and pouring is where all the issues had started. So you remember one thing, the root cause analysis is poor quality of concrete. Why is the quality of concrete poor? I don't know whether I have the next slide here. Okay, I have a slide there which explains what's the situation. If you notice that this is a 40-meter span, the depth of this box at the end is around, if my memory serves me right, around 2.75 meters or so, and about 3 meters at the mid cross section. It's a twin cell spine like this, so 2.75. I could be wrong with 2.75, maybe 2.5. You forgive me. If you check the dimension, you may find it. But if you look at it, it's a don't go by these dimensions. These dimensions are from another project. This is for illustrative purposes only. So when you pour the concrete cross section, it's a very wide deck. That was a 25-meter deck with almost 9-10 meters of deck. So quite often when you look at the shuttering arrangement, while in the outside you have a fixed shutter, your base is a fixed shutter. This side is a fixed shutter. The inner shutter, on the other hand, quite often is restricted to this. This is open at the top. So how do you pour the concrete in the segment? You first pour this portion, okay? Then you pour this yellow portion. That is basically the blue is poured first, and then these yellow green portions are poured next, and then the gray portion is poured. This is the most common sequence. You can have small variations in that. But the issue is, inside the segment mold, you pour the concrete from the top of the web. So if you see such a pouring arrangement, wherein this is closed here and you're pouring the concrete from here, you will notice one violation of a specification present in almost all the codes in all parts of the world, whether it is IS 456, whether it's IRC 112, whether it's Japanese standard, whether it's Euro code, ACI, ASTRO, every one of them has got that clause. What is that clause? That clause says thou shalt not drop concrete by more than 1.5 meters. And once you have 2.75 and you're pouring concrete from the top of the web, you're expecting it to flow past all this and come here. Your drop is much more than 1.5 meters. So what does that lead to? It leads to the fact that this corner could have significant segregation. Significant segregation because we have violated the drop limit. Now question comes, how do I overcome it? That only means you have to make your concrete pouring arrangement, your shutter arrangement amenable to limiting the drop. Now the question is, this is not the only project. I can take you to every project, including the 30-meter girder, post-tension girder and slab with only 2-meter depth of box is also poured like this. Okay, that's one part. Now comes the question. Once you pour it here, once you pour this portion, and when you pour it here, this blue concrete should have achieved a certain amount of stiffness. If it doesn't achieve the stiffness, then what happens is this will tend to heave. When under the pressure of this concrete, this will tend to heave. Now, what does this stiffness mean? That means you should allow the effect of the plasticizer to go away. Plasticizer effect is a time-dependent phenomena. From mixing in the batching plant to certain time only it will be active. So you should do a study before starting the segment pouring arrangement. how much time does it take for it to achieve the necessary stiffness? And then only start pouring. That means after pouring this, there must be a break. How much should be the break? That depends upon your type of plasticizer used, the loss of plasticity effect of the plasticizer, etc. Which means what? Your method statement should clearly identify for your specific cross section, how will you mix it, how much will you mix it, where will you profile, how much time interval, what workability you should achieve. Now, when you talk about the workability, it has to go past. Quite often, if you notice that there will be large pre-stressing ducts here. So why is it important to remember this? If you recall, at the place where this collapsed, it is approximately a similar distance here. The cable profile comes and there are all the cables become horizontal and bunched at this junction. What it means is, what I have not drawn here, there are a lot of pre-stressing ducts, and these ducts are fairly large in the sense they are, depending upon the design, it could be anywhere from 110 millimeter diameter to 135 millimeter diameter duct. Now your concrete has to go flow, you pour from there, it has to flow past all these ducts and come up to this. What is the kind of workability you will require to achieve that flow? It is not defined. It is not defined in any codes. You should have good practical experience for it. You should have a good concrete technologist on hand who will tell you, target the workability. And when you target, so therefore, when you're pouring here workability is different requirement because you're pouring directly from the top. It's only 2 layers of reinforcement. But here, since you're pouring from here, your workability requirement is different. Now, question is, unfortunately, if you look at most projects, everybody designs for one single workability. But if you have a one single workability, no problem. The best of the workability you do. But then you have to define what is the break you need to take between the pouring of the blue panel and the yellow panel so that you don't create a cold joint. At the same time, you avoid heaving. What it means is casting of the bridge cross section is a sophisticated operation. It is not simply mixing concrete, pouring it, and forgetting about it. So therefore, the issues that need to be addressed is concrete drop, concrete workability appropriate for the concrete area with respect to congestion and size of obstruction, adequacy of the vibration arrangement, whether you need to use needle type or form type, duration of vibration, 5 to 15 seconds, spacing of the needle vibration, not less than 500 mm. All these needs to be defined in the method state. I challenge, I don't know in the audience how many of you are at site, how many of you have seen a method statement which is specific to the cross section. Your method statement could generally be copied and pasted, and you could use it for a single cell box, multi-cell box, eye girder, anything they will fit in because they will all carry the same set of wordings in the same step. So with that, what happens is you end up having poor grade concrete here. Possibility increases to have a very poor grade concrete here. Now come back question. These failures are also in the same zone, but poor grade is not the only cause for it. This poor grade, when you combine with segment gluing operations problem, you have basically stacked up the whole game against yourself. What is a segment gluing operation problem? The segment gluing operation problem is basically that when you have a precast segment, before you join them, you have to apply 1 to 2 millimeter thick epoxy on both the faces. And after you have applied the epoxy, you have to apply temporary pre-stress to squeeze out the epoxy while it is still workable. While it is still workable. On 50 minutes, true statement, the duration available to you depends upon the type of epoxy you have chosen. Please remember, epoxy sets very fast. It consists of a two-part component, resin and hardener. They are just mixed prior to application. And depending upon the brand, depending upon the type, quality, the setting time is between 30 minutes to 50 minutes. Now the question is, obviously, the epoxy that sets with 50 minutes might be expensive. The one which sets in 30 minutes might be cheap. If you use 30-minute setting, then your whole cross-section process has to be finished in 15 to 20 minutes application. And then your pre-stressing application should also be finished within that, right? So that you still have 5 to 10 minutes spare available before the epoxy loses all its workability, right? Now the issue is also starting when the segment heights are more than 2 meters. So let us go back to this example. When the segment height is more than 2 meters, a person standing here may not be able to reach this. And a person applying from top may also not be able to reach certain portions here. So then what do you do? Then what do you do? If you leave it, on the other hand, if you look logically, what happens is you start application. This is the easiest because a person sitting there kneels down and applies on this interface. So that is the easiest. That is the oldest. That means the chances of that epoxy setting is the highest in all the cross section. And if it sets before you apply the temporary pieces, basically what you've done is the two match casting face that you've created, you've damaged them completely by introducing hard points. And when you introduce hard point, application of temporary prestress is only 0.5 MPa, very small force. You will not see the problem. But when you start applying the permanent prestress, then at these hard points, the stress level will be much higher than what you have theoretically calculated. These hard points have to crush and yield before the full section becomes effective. And therefore, in a combination of poor concrete, call it strength of concrete, and an enhanced strength due to creation of hard point due to gluing operation, your stresses locally can go beyond the actual in situ cube strength and the crushing will initiate. And once the crushing initiates, then depending upon the extent to which the strength shortfall is, it can have a very large amount of crushing or a small amount of crushing, leading to failure case 1 or failure case 2. So the question is, we still need to understand a lot about how we do a concreting operation. That is my submission to all of you. And application of epoxy, the code says 50 minutes. I would strongly advocate, if I ever, nobody can find fault with you. If you're contractually written, you have to follow the code, and code says 50 minutes. But my epoxy sets in 50 minutes. That clause is pointless. If my epoxy I have chosen for the project sets in 30 minutes, then I have to finish it in 20 minutes. And remember one thing, the road bridge cross sections are very large. They have large depth and large cross section. The area is more. You need more manpower, you need more arrangement, you need more mixers. So time is a very essential. Therefore, I have not seen a method statement which says I will monitor the time I take to apply. I will monitor when I have started application of epoxy, when I have finished it, when I have applied the temporary pieces. The method statements are so general in nature and at site, lot to be desired in terms of what happens there. And therefore, you end up with this situation of a combination of hardened epoxy concrete in locations and inadequate concrete strength locally. Okay, so good epoxy gluing arrangement leads to uniform load transfer, which all people know. It also fills up all crevices at the segment grout leakages and at the segment, and also achieves the filling up of the broken shear keys. Don't touch up the shear keys, fill it up with epoxy at the time of segment glue. Poor work leads to loss of match cast, presence of weak pocket where pull does not fill up the full crevices, and leads to serious problems of stress concentration and the hard points created to partly set patches of epoxy. And this acts like a trigger for local crushing of concrete. It acts like a trigger. It doesn't cause the failure by itself. And imagine that with higher compressive stress and having what we call it low strength of concrete, you have a problem situation. This is another one situation where you can see it's a girder and slab arrangement, practically no arrangement. A casting arrangement, you can see they cast on casting truss and then side shift it, bring it to the position. When you leave it for a long time without any stability arrangement, you are risking. Please remember, they all have a provision for it. This span is a 45 meter span, so there are intermediate diaphragm. Ideal situation would be as soon as you have a pair of girders which are temporarily braced, as soon as you have a pair of girders, brace them up with the casting of the diaphragm. At the very least, partial diaphragm is also good enough. That temporary bracing will act like a bracing. It will vastly improve the stability and you will not lose the girders like this, right? This is what they call it, crushing of the concrete has taken place just like the other one. the root cause are similar. The depth of the box, this box is around 3.5 meters deep. It's not as wide as that. It's not a spine and wing. It is a simple single cell box girder. And as you can see here, where the point where the girder is got the maximum eccentricity of cable, combined with poor quality, the crushing has taken place and the hog has happened. So this is one of the common recurring theme. Common recurring theme is non-stabilizing of eye girders, not managing the concreting properly in terms of the arrangement that you need to make based on the specific cross section that you're building. We seem to write very generic method statement. Now, this is another situation. This happened in Tirupati, where they had finished the assembly of the span and they were lowering the span. As you can visualize, the span was on a slope, longitudinal slope, and they were lowering it and onto permanent bearings. They had cast it higher, and with jack they were lowering. And as I mentioned earlier, lifting and shifting of the weights during this process is very important. And once this happens in a slope, the sliding mechanism and sliding prevention arrangement should be very meticulously thought of. In this instance, that sliding arrangement only fell and the whole girder slid one side and fell down, and they had to abandon this run and they have to reconstruct it. So stability is constantly compromised when you move, lift, manage, transport heavy weights. So you have to be very careful in your method statement, how you do it. Make sure that verification of equilibrium, depending upon your specific construction methodology and sequence, is done. And accordingly, the process is dictated and indicated to the site to carry out. This is another famous one here. It's the expressway in Dwarka, wherein actually, if you look at it, this looks like the failed span. Don't forget it. It is this span which failed. This span which failed and its concrete got crushed here. This is also spine and wing construction. And consequence of actually the middle leg was sitting on top of this end of it. And the moment this span fell, the middle leg fell. And because of that, the launching girder which was holding the segment weight also was lost, because this launching girder is not designed for carrying this weight with double the span. So, and the disease in this is exactly the same as what I showed you on the Sohna Road. Same issue, same deep cross section, same inability to concrete properly at the junction of the web and soffit. And the common theme across all this is the fact that the in situ concrete is vastly different from the cube concrete. And that is, I'm not at all suggesting that the cube results are first. I'm just saying that we are unable to transfer the proper methodology with which we see. Remember, cube is only a 6-inch by 6-inch unreinforced concrete. There's very little you can do wrong with it. You don't need to make what is called as a 5-star cube. All cubes will be 5-star, even if you do the normally or very poorly workmanship also. But the in situ work requires a lot of issues for us to understand from workability point of view, congestion point of view, vibration point of view, and the gluing point of view. We have a lot of still things. Please remember, this is the set of tragedies that we are seeing right from 2012, 2021, 8-9 period. And rest assured, the disease is not over. We are seeing it in the, I have stopped this collection at around 2020, 21, so that, I mean, they keep happening again and again. Awareness and correction is the only way for us, is to teach ourselves what we are doing wrong and rectify that. Right. There's another eye girder, and as I told you, stabilizing arrangement is a 45-meter span. If you notice this small prop, this girder actually weighs 160 tons. From what I remember from memory, this girder weighs 160 tons, and this is the stabilizing arrangement. And if you notice, they're all supported on temporary timber blocks, and these two are the only ones where the timber blocks were, instead of one large block, were made of smaller timber blocks. The problem with smaller timber blocks is you can never be sure that all the blocks are taking their equal share, which is what will be a convenient design assumption. And timber being a natural material, we cannot ensure that it has the same stiffness, same strength in all parts of it. So the choice of temporary supporting arrangement deviated. If you notice, they're all single large blocks here. But when it came to these two supports, they were an intermeshing of small cubes. I mean, not cubes, I should call it, maybe 4-inch or 4-inch square timber reapers block put into perpendicular layer. They were not even strapped together to make sure they act as one block. They could have done so many things. But at the end of the day, I still feel that the stabilizing arrangement that they make is extremely poor. You have to now realize that verification of equilibrium as prescribed in the code is very important. And that means the designers have to become aware of the exact construction sequence. The destabilization not only comes in the way they handle the girder, the way they position, the verticality, the type of bearing compression, but also how they assemble the shutter, how they pour the concrete, where will the construction drive load imbalance be. All these have to be, remember one thing, none of them is said not to be done. But unfortunately, we follow some rules in our books, we ignore many rules in our books. But first of all, from my point of view, rule books are meant for guidelines. You have to make sure that whatever methodology you think is convenient for you, make sure all the aspects related to that construction methodology is identified, verified for all the stability arrangement. And then go ahead and do it. Now, this is a failure that took place in the approach ramps of a flyover in Madurai. As you can see here, the girder that has fallen down is this. As you can see, it has got 5 cables, and they had only stressed 2 of them. Now the question is this, and as you can see, the staging trestles of this nature up to this height. The logic is defined by the choice of construction methodology. Why should you stress it at that height? After all, it's only 30 meter span. 30 meter span will maximum weigh 25-30 tons. You have got enough crane sitting there with which you can lift and place it on top. Instead of that, they chose to put up the staging, cast in situ, stress it. That's how they chose to do it. And when you have 2 parallel cables like this, the chances of transverse eccentricity during the stressing operation is very high. It's very high. And when that happens, the girders tend to deflect in the transverse direction. Of course, if you identify that the girders can deflect in the transverse direction and your staging supporting mechanism is designed to resist that transverse deformation and has adequate strength, both from transverse load transfer mechanism as well as buckling prevention mechanism, go ahead. But unfortunately, what happens is the temporary works I've done 5 times. So what is wrong with doing it again 5th, 6th time? That is the approach that we use. So therefore, the inadequate basing in the temporary one and associated with possible eccentricity during the stressing operation led to the dislodgement of the whole temporary works and the whole girder fell down. Sometimes the construction methodology you should think through and choose it carefully. There is no need to do convenience, sacrifice safety for convenience. Now, the only example of a steel structure that I could locate. So this is basically a 60 meter U-trough steel girder with the cast in situ concrete slab. So the incident happened. They had finished assembling of this U-trough. They had put up these some props for the shutter, and they were pouring the concrete slab. And once they had poured 2/3 of the slab, the whole thing had lateral torsion buckling, and it came. Now, I want you to notice one thing. It's a 60 meter span. And if you notice, from here to here, you do not see any supports. Now, those of you who have done steel concrete composite design would have realized that generally from an economy point of view, once a span crosses 35 meters or so, you end up having to do a propped construction in the composite construction. I hope I don't have to go through what is propped and unpropped. Basically, propped construction means you don't allow this girder to deflect downward under the self-weight of its own, as well as the self-weight of the slab that is going to be cast. You don't allow it to deflect. That is propped construction. This design was done as a prop construction, but you will notice that at the time of this failure, this is a newspaper photograph. There is no evidence of prop here. Remember, for this depth of the box, this U-trough is perfectly capable of standing its self-weight without. But it is not safe to take self-weight of the steel portion and the weight of the concrete. So that is what has happened. They have dismantled the slab, concrete, etc., and they have reused it. And this time they did it with propping, and the span is open now. So they did the rectification process. But the question is, the drawing apparently showed the props, but you can see this photograph shows no props. So this the kind of deviation from the design intent is risky, and therefore should be, I should use the word, it should not have been done at all. Right. This is an interesting case study. It's a Pardy flyover. It's about 7 kilometers long flyover. And on October 21, this span got dislodged. This span got dislodged. Other spans are still intact. And the span that got dislodged was constructed about 3 years before the failure incident. 3 years before that. So you have to understand why this happened at the background. This flyover, this unit was, I think, 3 or 4 span continuous structure, simply supported and made continuous with deck continuity. And these photographs have been taken from a YouTuber's video on YouTube. After the failure took place, they took a YouTube video, and I have extracted snapshot from it to explain to you what has happened. So basically what has happened, you can notice that you start the case with this span. This span is expanded, blown up here. If you notice here, this superstructure, there is no relative displacement between superstructure and the pedestal. That means from this I have surmised that this is the fixed bearing. Longitudinally restrained bearing is placed here so that this slab is not moving. So this is so-called a fixed pier for this 3-span, 4-span. All the other spans are what is called as a longitudinally free. So this is also longitudinally free, and originally there was a gap. You can see that this has moved this much. That means this much space, this edge has moved from here to here before it was stopped by the fixity of this bearing. So this superstructure has moved around 600 mm. So you can see this is the other end of this superstructure. So this has moved the same 600 mm. Now the span behind, now it has double the space, the original 600 and the 600 millimeter vacated by this by its movement. And when that happened, the far end of this span got dislodged and it fell down. Now question comes, what could have been done? All they need to have done is finished casting. As soon as they finished assembly of the superstructure, they should have done the deck continuity. It would have provided with the fixity bearing. The deck continuity is meant to restrain longitudinal forces. It would have prevented the sliding. The next question is explanation of why it slid. But the question, more important question is, why would anybody leave this deck continuity for a long time? For this, I have my only explanation is, these deck continuity, expansion joint, crash barriers, they are all treated as finishing items. In the payment schedule, there would have been possibly very little money to be spent, money to be gained by completing this task. So they would have decided, I will do it last. Now the question is that 3 years time interval allowed for the thermal movements to take place, and it has moved gradually. Nobody has noticed. Remember, this structure was in move motion for 3 years, and yet nobody. It tells you another thing, that though it's an active construction site, project is not finished. Hardly anybody takes an observation reading once they finish the span. Okay, another thing that we need to rectify. So the question comes, why did it move? The question comes, why did it move? So to understand that, I have exaggerated the slope. This bridge is almost on flat. If it was a steepness more than 2.5%, it would have slid because they're all pot and PTFE bearing. As you can see here, you can see the stainless steel shiny surface here, PTFE sitting at the bottom. So it would have slid off if the slope was more than 2.5. The slope is less than 2.5. Therefore, there is some friction. However, whenever there is a temperature rise or fall, it will always move towards the downward side, just like the way a caterpillar moves. It moves one direction. No, that's for visualization purposes. But all our assumptions that zero movement point is middle and movement take place in equally on both sides is valid only if the surfaces are truly horizontal. That is why you must remember that if you are installing bearings on, and I'm not saying that these bearings are installed in slope, but I'm just saying in a practical point of view, code also accepts within its tolerance 1 in 1,000 slope. as a tolerance level for potent PTFE bearing. 1 in 1000 slope is acceptable, but that slope will induce this motion. Imagine that there is a 2 degrees or 3 degrees rise in temperature. It tends to expand, and when it expands, it will not go in the higher direction. The expansion will go in the lower direction due to the way the frictional force is there. I've just tried to explain it. You catch it as much as you can. Now you can ask, in the contraction direction, it should go up. No, in the contraction direction, also it will move in the same direction, because when the contraction, the resistance forces are in the opposite direction, and then the fixed end again goes back to the upper portion. So in every expansion and contraction cycle, the girder moves little by little on the downward side. And it has taken 3 years plus for one span to move more than 600, 700 millimeters until it got dislodged at the rear end. The solution was simple. They should have gone and done the deck slab continuity correctly in time without looking at the payment schedule. Now the question comes, what could we have done to prevent it? Knowing that your girders are in slope and potential slopes, where you can do perfectly horizontal is practically not possible from a practical engineering point of view. You should have notes in the drawing to say that the deck continuity shall be established in not more than XYZ time. Nothing prevents us from putting such notes to make sure that the site is alert to such possibility. Now, the last case I have to present to you is a dry jointed, externally pre-stressed segmental construction from a place near Bangalore. In this case, its a typical span is around 35 meters, the longest being about 40. So basically, it's an externally pre-stressed, one of the rare examples, and it is a 2004-5 era construction. What it means is that the cable systems in 2004 and 5, we did not have the multi-layer protective systems of galvanization, individual HDP. Those things were not available. So what they had used was a conventional pre-stressing strand, and the corrosion protection was provided through cement grout. Now, what happened was somewhere around December 2021, during the transition from one operations and maintenance consultant to another, inspection was carried out, and they found that at least 12 cables have broken. Cables have broken in the sense, in the next photograph, you can see basically these cables should have been touching the bearing plate, but they have all, about 10 or 12 of them were found, and inside they found all kinds of distortion of the duct tube. They also found, take out the broken, the individual wires of pre-stressing steel, which are generally around 5 to 6 millimeters, have got reduced to 1 millimeter. And the breakage has been taking place slowly, that once the breakage took place, even the loss of the central core wire due to stress has gone unnoticed. So you can notice that there's a lot of loss of core wire and the others are sitting there. And now you will start wondering, Bangalore is a moderate exposure condition. Why is there so much corrosion? Why is there so much corrosion? Now comes a question. This corrosion is so high, not because of the fact that Bangalore is moderate condition. It is because of the fact that, one, you must all remember one thing, pre-stressing steel corrodes the fastest. Fastest in terms of, and it corrodes even faster when it is stressed. And it corrodes even faster when your alkalinity is non-uniform. What does that alkalinity, what provides alkalinity for the pre-stressing steel? The grouting. The grouting, basically a cementitious material, is an alkaline. If the grouting is non-uniform, you're basically aggravating an already bad situation. Now, all of them failure have taken place near the anchorage, especially the anchorages which were present in the inclined portion of the web. Because they were not grouted properly, many of them did not have the grout cap, and the end portion being ungrouted, what it led to is the cycle of cold and heat. The steel temperature chills faster, so the atmospheric air which goes in along with the moisture, it condenses on the strand. So you have access to moisture, you have access to oxygen, you have an access to dissolved oxygen, and therefore you have initiated the corrosion. Once you have initiated the corrosion, because corrosion in this instance is a electrochemical phenomena, You have differential potential setup because there's an alkaline region, there's a non-alkaline region. So you have a cathode, anode, all these are very conveniently positioned, and you have an accelerated corrosion taking place. So it has taken around 10-12 years for the strand to completely get corroded. Not all of them, because the grouting is also not uniform. Remember recently, 2 years back, when the old Kali bridge fell down, its origin is also to corrosion of steel under stress condition. And once the steel is stressed, you must make sure that it is grouted as quickly as possible and grouted thoroughly. That means the grouting process must be implemented more thoroughly, leaving out any possibility of air pockets, especially an air pocket which can have access to ingress of atmospheric air, because you need to constantly renew your oxygen supply for the corrosion process to continue. So therefore, while grouting is prescribed, I am not sure that the quality of grouting in our country is all that great. We have seen many of these failures of this nature. So if you improve that, of course, all the strands in the cables are being replaced one by one. The project is almost finished now. It is going to be ready to open for full traffic. 100%. That means they have ended up spending another about 50-60 crores in the 3.5 kilometers. All the strands, all the cables have been replaced with the more modern stay cable type of galvanized strands with grease filled HDPE sheathing. Okay, so what have we seen in all this? We have seen there's a common thread. We seem to know all the right processes, but we seem to give it a go by for convenience. Not always, but the fact that these are very expensive infrastructure, even one failure is one too many for us. What can we do about it? So what are the learnings we have taken? Basically, you can have causes of failure due to design, temporary work, quality of concrete, quality of workmanship, inadequate precautions, and unsafe practices. And most importantly, most of the failures happen during construction. Most. Okay. So what do we do? So we can improve the design control. This has been significantly achieved. I'm not saying it's 100% at all. All those organizations which have a strict design control, wherein there is a check, there's a review, there's an approval process, which are honestly done, you will find that design errors are quite often trapped in the offices. However, design errors due to improper detailing, that is something that we are grappling with, because we do not have for the quantity of work that we do in our country, we do not have adequately trained manpower. And detailing is something that is considered as a drudge work. So we hate it. We avoid doing it with the thoroughness that it deserves. So we may be able to control in the broad sense design, but when we miss in the detailing, we'll again sow seeds of potential failure. Construction control, as you have seen, a lot of these failures have happened because they didn't have a systematic way of working. They are doing all on ad hoc basis. An interesting story was told that, if somebody describes to you, all those who live in Bombay or Delhi or Chennai, where there are a suburban train system. So somebody said, please write a method statement to travel from your home to your place of work using the suburban rail system. So the method statement read like this: do the preparation at home for going to office, collect all the things that you need to take the office, go to the nearest suburban station, wait for the train appropriate to your time. When it comes, board it, go to the destination station, get off, and from there travel to your office and do your work. In terms of covering it beginning to end, it seems to cover everything. Now, if you look at it, somebody asked a question. In this whole procedure for traveling from home to office, the method statement does not tell anything about buying tickets. So the answer came, I have traveled for 6 months without ticket. Nobody asked me, therefore it is perfectly all right not to buy ticket. Our work methodologies are like that. I have done 50 girders, launching girders like this. Nothing has fallen down. Therefore, this method statement is correct. So in as much as gradually diluting our rigidity, we have made our method statement so general that we are basically uncontrolled activity is what I would call most places, not all. Some of them are doing work, kudos to them, but vast majority of them still have got very poor control. So this construction control improvement is very important. And the last and final, material and concrete production control. This is where we have a lot of work to do, a large amount of work to do. It includes check from procure. We may do the procurement, production part is okay. Placement, handling stages leave a lot to be desired. Okay, so that we need to improve. But at the end of the day, why are all these things happening? Because designers have very little understanding of how site works. And site engineers have very little understanding of how to take design decisions. And unless we have both of these improved, we are going to face this problem again and again. So site engineers need to absorb the principles of design aspect, and the design engineers need to absorb how the site works, and therefore help them do better job. And so I'll close it with that. Thank you. Is there a time for question and answer session if you have?
Yes, please. Excellent presentation. Before I ask the others to ask, please tell us something about the monitoring part of these. See how to monitor during the design and construction stage, and what type of monitoring that we need to check that the structure remains safe during construction and post-construction.
Okay. Let's start with the design part. Design part is a little simpler because it is based on office-based work. That means basically what we need to have a capacity building within design organization, which I feel most of them are doing a reasonable job. I'm not saying the very good job, but there are reasonably good job is being done. But thereafter, what is happening is once it comes to the construction side, if you look at the way, as I keep mentioning again, our procedure, if you look at our contract, how do you say the concrete I am producing is acceptable? In an Indian contract, I'm not talking about the contract worldwide. In an Indian context, the only way you can accept or reject a concrete is purely based on passing of cube strength or not. There are no other criteria fixed in our standards. And that is very easy to pass. That means we have set our benchmark at very low level. We have not set up any further benchmark to say, how do I make sure that my field work is commensurate with my design expectations? We have got no standards like that. And if you ask me practically, it's not possible. You cannot cover all the situation. And this is where, now the question you can ask, after all, we are taught concrete the same way as the rest of the world. We also produce in the same way. Why is it that we face this problem and say in a developed world, we don't face this situation? The main reason for that is if you look back at the way they do the contracting, their contracting is not based on compliance. Their contracting is based on responsibility. I may give you a contract, you may have to follow certain standard, but that doesn't absolve you from your responsibility to finally giving me a product which I have paid for. Okay, we don't have that. I'm paying you for product which complies with the standard, and I always comply. It is very difficult to fail from the standard, but at the same time, I'm not delivering what I have to deliver. So, if you want this to improve, you have to change the way we do our business, our construction business, the way we construct. I don't mean to take this discussion in different direction. We need to professionalize our practice, wherein we are responsible for all the decisions we take. Today, nobody is responsible because if the structure fails, ultimately everybody will say it's the government is responsible because you have set up the IRC specification. I have complied with it. If they are inadequate, what can I do? Okay, so when it comes to, and I also feel that we have diluted the importance of concrete technology in the sense I don't find in most project site, I don't find they're large value project. When I say large value, means somebody who's producing 1 lakh, 2 lakh cubic meters for a project. I find it I very rarely find somebody a concrete technologist who says your project has these situation, at this place you do this, at this place you do this, at this place you do this. For us, one shirt fits all kind of a solution. That's the biggest problem that we are facing. And naturally, when we talk about concrete technologists in that large number, it is not it's a specialized field. I at least feel every organization should have one or two who must be given the what do you call it, the responsibility to monitor and correct the processes wherever they are going wrong. I have no solution. I am more interested in making awareness first. Once we have the awareness, yes, these are all going wrong, then more and more people will think about it, how to set right. Rather than if I give a solution, rest assured, 5 minutes later, everything will be forgotten. It is like this. We have got so many good practices written all over the country, but we tend to say it's inconvenient for me, so I give up. So that approach has to be changed.
Right. Vikas, other question, just quickly, please.
Yeah, sir. There is also some Bhomik sir is here. I think we must.
Okay.
Bhumik,
Yes,
come forward because you are also expert in Bridget.
Okay. I think we have had just a treat. Excellent presentation, PGV. Very, very impactful, very, very educative, and informative. And of course, this is not a surprise to me because I know that I was expecting this kind of a delivery. I mean, you have the reputation of giving such wonderful presentations. Very nicely explained the various case studies, the anatomy of failure, and I think very beautifully gone into the details, how this failure occurred, how the failure could have been avoided, what provisions of the code actually is being sort of quoted by maybe the consultant, and I think you have also highlighted some prevailing clauses also of IRC 78, which should be read cautiously.
It should be deleted.
I mean, yeah, should be deleted rather. I think PGV, that clause is deleted already, as per my knowledge.
The new version. No, unfortunately,
the new version
2014 new version is translated to IRC 112, so it will not come.
It has not come. It has not come. I mean, the translated version. But anyway, the point is very well taken. And by the way, I also, I was one of the panelists in that failure of that bridge which you have shown. I think where the brackets have failed on both sides.
Correct. Karamnasa Bridge.
Karamnasa Bridge. And I was there at site just after the very next day. On 31st of December, I was there. I remember, seeing that failure and very, very interesting cases. I have a couple of issues I just want to share on your presentation. Firstly, I think while describing about that failure of that curved flyover in Surat, I think Surat, you mentioned about, the code, the stability part is not covered, subsequently covered. Was not covered, but
I'm not justifying the ignorance. Yeah. I'm just telling I'm aware that there were very different practices at that time. Now it is standardized.
Yes, I know. So I just want to use this platform to basically, highlight what exactly you have said, but I just want to underline that, these codes and standards are just the minimum requirements for safety. But most often I found that, these codes are only taken as the only textbook you are supposed to read after you pass out from the college. That is a problem. They are only intended to be some foundational guide or some prescriptive bare minimum requirements. They are not basically telling you the behavior of the flow of forces and how how the structure stability is to be checked. Today, we have an IRC code. Suppose you are designing another structure which may not be covered by IRC and you have a problem of stability. These are basics. These are to be checked irrespective of whether you have a code or not. This is one. Secondly, you also showed one and very nicely explained about that spine beam construction. I think probably that was, if I remember correctly, it was in Dwarka, though you did not mention. But you explained very nicely about the sequence of pouring of concrete and how the concreting one should take care to ensure that the design is executed properly, without any problem. Here, I just want to add one more thing that the reverse is also true. Sometimes the designer is giving something which is not very construction friendly, and then construction becomes difficult and there is a mess up at site. So it goes both ways. I think as a designer also we should give details which are easy to sort of construct, and such problems, if we envisage during the design stage, we must highlight. I think you mentioned that also in one of your presentation. We must highlight it in the drawing, what we envisage in the design and how at site it has to be taken care. And the last thing which I want to mention, you also touched upon this Madurai flyover collapse. And because I was one of the panelists, expert panel there in that investigation. So let me inform that that flyover collapse is not just because of the instability during pre-stressing or due to the staging and all. What happened is actually there was a sequence of the girder has to be lifted up. While lifting up the girder, have used a single jack on both sides. So there was an instability during lifting. And of course,
okay, so it comes down to the verification of equilibrium during the handling.
Exactly. And they claimed, there were vehement objections when we wrote that, and the contractor claimed exactly the way what you mentioned, that we have already done 30 girders like this in this very flyover. Nothing happened. And so therefore our method statement must be correct. So I thought I will share that. But overall, excellent presentation.
So basically, everybody is saying buying ticket is not necessary to travel on some until you get caught.
Correct. But excellent presentation. The way you have explained the design and the construction and the mitigation measures, I think this presentation we must circulate. If you have a record, YouTube record, I think we should give very wide circulation to this. And I would request you to also.
You are recording this, so I leave it to you.
So I think we will do that with your permission.
I hope I'm not getting caught with any copyright issues. I am trying to use the photograph from public domain as much as possible.
No, I think it serves the basic purpose of educating people.
Put in our class magazine.
That's a different. I will take it up later. But one more thing, if you can share your handout of the presentation,
I'll send it.
It would be great.
I'll send it. I'll send it to Dhawan Saab and.
Thank you, PGV. Very much enlightened, I tell you.
Right.
Great. Okay. Any more questions, Vikas?
Sir. There are a few questions, sir, in the Q&A. Mr. Suresh Tripathi asks, IRC 112 mentions about the maturity methods. Is it being used?
What method?
Maturity methods.
Maturity method.
Yeah.
Maturity.
Is it being used? Yeah. Is it being used extensively to know exact concrete strength? What is your experience?
See, the point is ultimately that my point was not to say that concrete's maturity with age is a well-known phenomenon. It is covered in all the textbooks. It's also covered in our IRC 112. However, please remember, there's a big difference between how do you establish the maturity level? Same old cube test. Unfortunately, you do not have a mechanism whereby you know what is the in situ strength. And our decisions are for in situ construction. What is the status in site rather than what is in cube? Our cube will always give you one information, but what is there actually inside the structure is a different one. That gap is where our biggest problems lie. So therefore, maturity is used to prescribe these stressing days and sequences and things like that. It's validated by cube strength, but according to me, any design which does such tight work is bound to fail for simple reason. We don't have adequate quality control at site to achieve that precision. I feel you should try to do as robust a design as possible. But I know in today's world, economy and all those are the buzzwords. I'm not saying they are wrong words, but I'm saying you practice it. If you are, it is like saying that I also want to throw javelin like Neeraj Chopra. I have 2 hands, I have 2 legs, I can also throw. No way. He is trained for it for life. Therefore, he's able to throw it 100 meters. I may not be able to even throw, but the point is because I can physically capable doesn't mean I should attempt to do it. That's kind of analogy I would like to give you.
Thank you, sir. Another question by Mr. Rama Jogaya Shastri. Any international court talks of casting a sequence of bigger box girder segments?
No, it is generally left to the contractor's prerogative in an international scenario as to how he will cast it, because he is totally responsible for giving a finally performing end product. International contractors are not bothered by the process. They are bothered by the end product. Your end product must meet my specification, your design requirement. That's all that they require. So you are free to engineer whatever you want. They don't put restriction, no, you shall do it. I only describe the various processes that are used in India. I'm not saying these are unique to India. Some of the outsiders also follow it, but then they have different checks and balances.
Thank you, sir. Mr. Bedibel Raja asked, please explain the CMRL Phase 2 PSC 1 girder collapse in front of L&T Chennai office entrance.
Okay. If you are familiar with that project, basically what happened was, if you look at that structure, it's a double decker. That is, the upper level is a metro with U-trough solution, and the lower level is a road bridge, which is a divided 4-lane, 2-lane structure. Now, a typical span on that whole flyover was a 25-meter span, for which the road bridge was consisting of 3 RCC girders. Now, in front of the L&T campus, they needed 2 spans of 35 meters. Now, they cannot alter the road level. They cannot lower the pier cap, because one will encroach into the clearances below. So how did they manage the longer span on the same structural depth? Was by converting the RCC girder for the smaller 25-meter span to a PSC girder for 35 meters. That is one change they did. Second thing they did was that they changed the number of girders from 3 girders for the 25-meter span to 4 girders for the 35-meter span. So what did this happen? What did this lead to? The pier cap for the lower road level is the same, because the carriageway width hasn't changed. So pier cap width was the same, but the 4 girders occupied more spacing. So on a 3 girder spacing, they had a bracing system until they cast the deck slab on both sides. Unfortunately, for this 4 girder system, the 4th girder came to the edge of the pier cap. So on that girder, they couldn't brace it on the other side. They only had a tension, and that is a horrible method of bracing. That is a horrible method of bracing. The way they should have done was, they should have, which they followed subsequently. What they did was, they extended a temporary steel pier cap, and then they had bracing for the 4th girder also from both sides, or they quickly cast the diaphragm. Otherwise, they were holding the girders for a long time and waiting for the diaphragm to be cast. So that is the main reason why that girder toppled over, because it had no stability.
Thank you, sir. Mr. Suraj Singh Mehra asked, to what extent does a designer remain responsible for design integrity once construction begins, particularly when value engineering site constraints or contractor-led changes, poor quality come into play?
Okay. A designer is responsible for all his work. You can prove that this is a design fault by reviewing the design fully and finding out whether there has been omission from his part. Okay. Once a design has been completed and it has been reviewed by a peer or a person more skilled than that and said, yes, this design is safe, one, compliant to standard, two. Once this happens and it goes to the construction, then you can find hardly any liability for the designer. But if any one of these stages, that there's an omission and commission by the designer in the supply of the details and the drawings which are inadequate, then yes, irrespective of, you're asking whether this due to circumstance. Now the question comes, now if you now, we are coming back into the debating, why do we have this mode of contract administration? Let us put it this way, why did India opt for design and build? And the design and build is a only for very, very special bridges in the West, it goes for design and build. For run-of-the-mill structures, it's only item rate contract because they have a standardized construction. But in India, for everything, we go on design and build. Why? If you answer that question, design and build, by its very nature, gives you the least standards. Why? Because as an EPC contractor, now I'm talking like a contract. I don't have to do the best standard. Nobody, you're not paying me for producing the world-class standard. You have set your benchmark at so low level, I have to only got to comply with that. Okay, so once you have set that EPC mode of contract, you will always have your set of competition. Everybody is bidding lower and lower and lower and lower. So in that process, what is happening? What suffers? What suffers is the quality of both the concept as well as the execution. I will be only interested in supplying you with a compliant design. And remember, throughout the world, the prescribed engineering standards are the bare minimum. They are not the maximalist standard. That is why in an EPC contract where they want a higher than minimum standard, they will have special conditions which say, I want this, I want this, I want this. Unfortunately, we don't do that. We have gone for an EPC model where we want to cap our price. I'm taking from the government basically wants to cap the price. And then you let the competition loose among the bidders. And we are such a large country. Everybody feels I can also do the work. So you are basically encouraging a free-for-all competition in which what is the only compliance requirement? Minimal standard, not the maximum. So you are going to face this risk again and again.
Thank you, sir. I think Devjyoti Paul sir has same question. He asked, in EPC contract system, addition of extra concrete steel puts the designer in question by the contracting agency for commercial points of view. How to justify designers' engineering judgment going above the code?
That is where, if you recall, I have mentioned the last way to mitigate it, there must be a good dialogue between the designer and the contractor. There must be. If each one works in a silo, I will produce, if I am a designer, as a designer, I will produce a solution that is most convenient for me. And if I am a contractor, I will expect a solution which is most convenient for me. I don't care about your convenience. And if I am a economic point of view, I will expect a design which has got the least cost for it. So now if everybody is optimizing for themselves, all civil engineering decisions are compromise. All civil engineering, because there is no one single correct answer. In our civil engineering, bridge engineering solution, there are multiple correct solutions, and each of us chooses the one which is most suitable for us, or whoever is the most persuasive among the two. So once you have a triangle of people, there is a contractor, there is a financier, and there is a designer. They must all gel together to come up with a final good solution.
Thank you, sir. Mr. Raghuveer asked, why box girder segments are not casted upright, keeping cell vertical?
What do you mean? I didn't understand the question. They are cast upright.
Mr. Muhammad again means write something. It will be more costly to vertical match casting. I think he has.
Oh, you mean the other way around?
Let's now try to.
Yes, sir. This is the last question by Mr. Yuvraj. If the durability limit state checks in IRC 112 are satisfied only by design but violated by construction variability, should bridge engineer introduce a post-construction durability reliability check analogs to load rating before accepting a structure for 100 or 120-year service life?
That is the question that has to be agreed between the owner and
Yes.
the designer. For example, I will give you one example. In Chennai, there is a project that is being implemented between Chennai Port to Madras. It's about 25 kilometers elevated corridor. It's a double decker for about 14, 15 kilometers or so. So there, after looking at all these issues, there is a specific condition put that there will be, because we don't have a very well-defined NDT tests, which will establish the quality very thoroughly in terms of both strength, density, etc. It's a very tedious process otherwise. An indirect measure has been incorporated in the contract. But I'm not saying that will guarantee good quality work, but it puts one more level of check on the contractor. The question, what I am worried about is that particular standard on the basis of which this entity is prescribed, you can read partly or you can read it completely. If you read partly, even with that, you can say a substandard work, you will declare it as a good quality. But if you read the standard thoroughly, you will catch the substandard work. And if you don't catch the substandard work, you will not give a direction for process improvement. See, all the idea is once you detect the variations, that means there is inconsistency in your processes. So you have to go back and set your processes right. And that kind of a feedback, if you have, there'll be a gradual improvement in the quality. So you can prescribe higher quality standard, but depends whether your owner likes it or not, because it's a headache for everybody.
Now, I think no more questions, and then Mr. Professor Venkatram, excellent presentation. The message from his side is very clear that for proper mitigation measures, we have to do things holistically, design control, construction control, material, proper quality assurance, quality control. There's no shortcut. So we need to upgrade skill of workers and engineers, and then there has to be proper integration between the design and the construction. Because the EPC contract, as he said, will not help us in giving the durable structure, which can last.
It's a least quality contract. It's a least quality contract.
I fully agree with you. So proper quality assurance, quality control, and proper structural monitoring will ensure the good structure that can last for even 100 years. So thank you once again, Professor Venkatram, for sharing your knowledge and experience.
And I'm sure I would like to thank all the audience for patient listening. And I wish it was interactive face-to-face, but the times are such that even this is good enough for me.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, Vikas. Thank you.